Our third video for Chapter 3, Scatter Plots and Correlation, deals with least squares regression line, right? The least squares regression line. Okay, so we've got a couple of students. They want to investigate if tapping a can of soda would reduce the amount of soda expelled after the can has been shaken, right? And the whole idea on tapping a can of soda would be, right, where you might tap the top so that it doesn't spew out a lot of soda onto you. Okay. For their experiment, they vigorously shook the can, 40 cans of soda, and randomly assigned each can to be tapped for 0, 4, 8, or 12 seconds. Then, after opening the can and cleaning up the mess, they measured the amount of soda left in each can in milliliters. Right. Here is the scatter plot of the least squares regression line, right, where that least squares regression line is. And if I'm looking at this particular piece, I did not have my hat drawn on here, but I do know the hat is on the PDF that you would look up. But in any case, right, this least squares regression line is going to be that the amount of soda remaining is equal to 248.6 plus 2.63 times the tapping time. Right? This least squares regression line should always have this hat over your predicted variable at the front, and you should always talk about your explanatory variable over here. Okay, so we'll work through these problems right quick. The first one: predict the amount of soda that remains in the can for a can that is tapped for 10 seconds. So in other words, we're trying to say, hey, what's going to be that value that if I happen to tap a can for 10 seconds? And that amount is just going to be simply substituting in. So 248.6 plus 2.63 times 10, and that's going to be 274.9 milliliters, right? So this is the predicted amount, right? This is how much, right, we would predict there to be, okay? What if, right, this should be an F. What if your prediction, or no, it is and is. What is your prediction if tapped for 60 seconds? Are there any issues with this prediction? Well, try it out, think about it, and then unpause the video. Well, that prediction would be the amount of soda left is equal to 248.6 plus 2.63 times 60, right? Because the tapping time is now 60 seconds. And that's going to be 406.4 milliliters. Now, that might not seem like anything too bad, except when you consider the fact that a can of soda only holds 355 milliliters. So we can't be confident in this data because a can only holds 355 milliliters. Also, 60 seconds is well outside our collected data range of 0 to 12 seconds for our explanatory variable, right? We just did 0, 4, 8, and 12. That's all we had data for. We have nothing remotely close to 60 seconds of tapping time, right? Whenever you use a regression line to make predictions using values outside of our collected data range, right, and the collected data range of the explanatory variable, that is known as extrapolation. Okay, and extrapolation is always a little tricky and fickle thing because we don't know if the pattern holds. Okay. So in general, extrapolation for the purposes of our class is not a good idea. However, if you look into numerical analysis techniques and you're going to go do graduate work in finance and business and you're going to go be an actuary and do these other things, you're going to learn about lots of methods for extrapolation and other predictive techniques that do involve some advanced mathematical thinking. Okay? Very, very cool things. But for our purposes, extrapolation, right, using the regression to make predictions past our data range for the explanatory, not generally a good idea. Okay. Then, part C. Interpret the slope and y-intercept of the regression line for the soda tapping. This is a very common question, so make sure that you understand the following. And that is that the interpretation of the slope for our particular situation, right? Our particular situation, here is explanatory, here is response, is that the amount of response remaining, right? The amount of response, right? So the amount of soda remaining, right? Increases, decreases, whatever, by value of slope on average for each additional units of explanatory, right? And then of explanatory, right? So once again, so the amount of soda remaining increases by 2.63 milliliters on average for each additional second of tapping time, right? Once again, your response, directionality, amount, that's your slope, right? On average for each additional explanatory unit, explanatory variable. Okay, so amount of soda remaining increases by 2.63 milliliters on average for each additional second of tapping time. And what about the y-intercept? Also very important. All right, so for the y-intercept, we'd say, hey, the predicted value for blank, the predicted variable, is blank, y-intercept, when blank, the explanatory variable, is 0. So in other words, for this situation, we would say the predicted value for soda remaining is 248.6 milliliters when tapping time is 0, right? So that y-intercept is that the predicted value for soda remaining is 248.6 milliliters when the tapping time is 0, right? The following is an important caveat. And that important caveat is if we are extrapolating to 0, right? So if 0 is not within our realm of the data collected for the explanatory variable, right? So if we're extrapolating, that y-intercept may have no meaning, okay? And in fact, you're going to see that example when we do the Mentos example, Mentos and Diet Coke, okay? So, another calculate and interpret. Let's do that. Calculate and interpret the residual for the can tap for 4 seconds with 265 milliliters of soda left. Well, what would that be? That interpretation and the calculation of the residual is as follows, right? The residual is y minus y hat. What does that represent, right? Well, if I've got this scatter plot, okay, then my points that I actually have as my data are my y's. Points that are predicted on my linear regression line, right? So these points that are predicted on my linear regression line here, right? Those are my y hats, okay? So if I want to calculate y minus y hat, in this situation, y is 265, y hat is 248.6 plus 2.63 times 4, which is 259.12. So y minus y hat is 265 minus 259.12, which is 5.88. So what is that interpretation? That interpretation is that there was 5.8 milliliters more soda left in the can than was predicted by our model for tapping of 4 seconds. Okay? Use the same idea to try E. Pause the video, try it out, unpause the video, check your answer. Okay, so y is 252, y hat is still 259.12, y minus y hat is the residual, that's negative 7.12, right? The residual could be positive if my actual is above the regression line, residual is negative if my actual is below the regression line, and we can say that there was 7.12 milliliters less soda left than was predicted by our model for tapping of 4 seconds. Okay? It is very important that you understand that if you have a good regression line, you're going to have positive and negative residuals. We'll look at the details of that in another video. Okay? So then finally, it's very important to be aware of the notation and terminology used for regression model predictions and interpretations. You have y hat. You have to talk about predicting. You have to talk about the context. Right? So in this situation, right, where soda, right, and once again, I don't know why it didn't put our hat there. So notation-wise, right, we were using soda hat, right? So where soda hat is the predicted amount of soda remaining after tapping the can for some amount of time, right? So y hat in this case, our variable response that we are predicting, soda hat. This is a predicted amount, not the actual. It's a predicted amount, and then what was the context of our situation. Okay. Make sure you're completing your work, doing your exercises, ask questions for clarification. Okay. We have more videos to help you out on the other topics.